Okay, this is a great question, example 5.3.6, because it ties together everything that we've talked about really in force so far. So the first thing you do is you look at the free body diagram, and you can evaluate this free body diagram to figure out a couple of things. And we're going to do that in just a second. But it says, what is the acceleration of the car? So I know that the acceleration is what I'm trying to find. Now you have a couple of options in terms of calculating acceleration. The first one is you can use if-that. But if you look, there's no information in terms of initial velocity, final velocity, distance, time. There's really none of that information. So really, the only other option would be the sum of the forces equals mass times acceleration, or Newton's second law. So let's look at the information that I'm given. I've got this free body diagram. So what this free body diagram allows me to do is it allows me to calculate the sum of the forces. So what I do is I start with the top and the bottom. 50 up, 50 down, they cancel, they're gone. Okay? 100 right, 40 left. So what I do is I take the larger one, which is 100, and I subtract the smaller one. And what I do is I get 60 newtons to the right. That right there represents the sum of our forces, 60 newtons to the right. Now, there's one other trick to this question. I need to know the mass. Now, a lot of people look at this free body diagram and say, oh, look, the mass right there is 50. That is not the mass. Remember, on a free body diagram, what this bottom arrow indicates is not the mass, but instead the weight. So, in our case, the weight, Fg, or it labels it as W on this particular graph, is 50 newtons. Now, how that's going to help us is there's a relationship between weight and mass that we've already talked about. We can assume this car is going to be on Earth, so we can say that Fg is equal to mg. Or I can calculate the mass by saying, hey, if I take that weight and I divide it by gravity, that right there would give me the mass value. So if we have our original equation, sum of the forces is equal to, instead of mass, Fg over g times the acceleration value. So what I did is I just substituted this value right here in for m. So we can go ahead and take a look now, and we can say, I got to move this over to the other side. Well, let's plug in our numbers first just to make it a little bit easier. So we have 60 newtons, which was the sum of our forces, is equal to the weight, which was 50 newtons, over 9.8 times the acceleration value. So, to isolate A, multiply both sides by 9.8 and divide by 50. When you do that, cancel out there, and we can move it over to the other side, and we can say 60 times 9.8 divided by 50 gives us an acceleration value of 11.76 meters per second squared. Now, in this particular case, it might be useful to go ahead and say, well, let's make sure the units match up. So remember, I have the sum of the forces. That is measured in newtons. I also have the gravitational force, which is also measured in newtons, divided by g. G is the acceleration due to gravity, so all accelerations are measured in meters per second squared. And then the acceleration that I calculated was in meters per second squared. So when you do that, cancels, I'm left with newtons equals newtons, which means that what I did is valid. So the answer is, of course, 11.76 meters per second squared.